when you talk about climate, there is always way more to be said in a short time than is possible, so I have to skip over a lot of topics really quickly, and that's kind of inevitable. So this is what the hopscotch court will look like today. I'm going to talk about the duration of the pause that is mentioned in the title. I'm going to try to clarify that the pause itself doesn't actually matter all that much. It's not the pause, it's the flaws that matters. In other words, what this is teaching us about models and predictions, and then carry over from the climate modeling side to the economic modeling side, the integrated assessment model world, and then from that make some conclusions about economic policy related to climate issues. Okay, the duration, let me show you what we're talking about here. So this is a graph probably familiar to a lot of you. This is from the IPCC report that came out in the fall. It's a summary graph showing the progress of globally averaged temperature measures around the world from 1850 to the present, to 2012 in that case. And 3 different series there are averaged together. So you can see there are lots of pauses in the record. There are lots of spikes and jumps and dips. The main features over the 20th century, there's the run up from about 1900 to 1940, a declining portion up to about 1980, and then from 1980 up to the present, although you can see after the late 1990s, there's a hint there of a leveling off. This graph isolates out one of the 3, the Hadley Center HADCRUT 4, as it's called. That's the 4th generation combined land and ocean record from the Hadley Center, running from 1850 to 2013. And again, you can see it's not an even upward path by any means. It has 3 distinct phases in the 20th century. But at the end there's something that looks like a leveling off. And that's what people refer to as the pause. Now, this graph shows us a bit more detail about the end of the record. This starts in 1979 and comes up to the present. That says 79 to 2012, but I just downloaded the data 2 weeks ago, so it comes up to 2014. This data is taken by what are called the microwave sounding units on weather satellites, and it's processed by remote sensing systems in California to produce a temperature record for the lower troposphere. And in this case, you can see from 1980 to the late 1990s, there's an upward slope, and then after that, it levels off and seems to dip a little bit. So, if you go back to the whole post-1850 record and just put a straight line through the whole thing, you'd get a picture that looks something like that. So there's an overall upward trend in the graph. And around that upward trend, there are lots of longer-term and shorter-term variations and cycles and so forth. That upward trend, that's not fitted using least squares or anything. I just eyeballed that. I'll show you more precise numbers shortly. But the point here is if you point to the pause at the end, somebody would justifiably say, well, the pause at the end doesn't really matter. You need to pay attention to the long-term trend in the data as the indicator of what we're talking about. And that trend there isn't all that large. It's about 0.07 to 0.08 degrees per decade. So it's a little under 1 degree per century in that record. Now, if I move the start date of the sample forward, then the trend might change a little bit. So if I move the start date to the year 1900, the trend still has more or less the same slope, maybe a bit of a bigger slope. If I move the start date to 1950 there, then the slope is even higher, and you can see what's going to happen if I move the start date to the 1970s. The slope would get even higher, but then if I move the start date to the late 1990s, then it goes down to 0. Let me show you the same thing, but a bit more precisely. This graph is generated by changing the start year of the sample along the horizontal axis and then computing the trend in the data through the rest of the sample. So the black dot indicates the size of the trend, and if I start the sample in the year 1900, you can see the trend there would be about 0.07 degrees per decade, and then the 2 gray lines above and below it, that gives you the 95% confidence interval around the trend. So the trend magnitude is extremely constant if you start the data anywhere up to about 1940, and then from 1940 into the 1970s, the trend magnitude grows, as you saw in the previous graph. But then after 1980, the trend in the data begins to decline fairly sharply, and so we could ask, at what point does the trend become statistically insignificant? And that means, when does the lower bound of the confidence interval cross the zero line? And that will happen, in this case, in 1994 in this record. So a sample starting in 1994, this is a monthly sample, from 1994 to the present would have a statistically insignificant trend, and from 2001 onward, the trend itself would, for the most part, be negative in the data. Okay, so that's the surface record. If I do the same thing with the satellite data, the trend for the past 26 years, or any shorter duration, would yield no significant warming trend. So as far as the duration goes, we are talking now about a couple of decades, at least. And so it's not a trivial length of time. Against the whole of the post-1850 period, though, it's still a fairly short period. So for that reason, on its own, it doesn't mean anything. And when we hear people responding to the talk of the pause by saying, yes, but it's the long-term upward trend that matters, that's a valid point. But there is something here that does mean something, and to show you what that is, we have to look at another graph from the IPCC report. This is figure 9.8. Chapter 9 in the IPCC report is their discussion of the performance of climate models and their evaluation of the quality of climate models. GCM stands for a general circulation model. It's the category of very large, complex climate system models. And what you have in this graph, all those little colored wiggly lines are the outputs of individual model runs, and then the red line is the average of all the climate model runs, and then the black line, that's the observational data that I showed you earlier. So we're interested in the comparison of the black line and the red line. And you can think of the red line as kind of the summation of the mainstream thinking in climatology. It takes all of that modeling activity and all of the ideas and the hypotheses and the theories represented in the models, and that red line is the central tendency that they all work around. That's the average output of climate models. Now, it's a pretty good fit, but the IPCC itself will be the first to tell you, don't read too much into that, because of course the models weren't run back in the 1800s. The models were just run fairly recently when they could peek at the answer. So the modelers had the input data, the greenhouse gas levels, the solar variations, the aerosol pollutions, the volcanic activity. Those are the inputs into the climate models. And they knew what the temperature record looked like that the models were supposed to match. So with both the inputs and the outputs, the models can be tuned and tweaked and set up so that they match over the historical period. Excuse me. So of course, they should line up fairly well together. And looking over the earlier portion, at least the portion up to 1980, you can see that the black line and the red line keep touching each other. They never go too far apart. There's only one interval where they go apart for a maximum of 9 years, but otherwise, they always come back into contact with each other. Whenever they touch each other, that means models, observations are saying the same thing. So you don't want to have those lines moving apart for too long, because that would indicate that now the models and the observations are diverging. When we go to the end of the sample, though, that's where the pictures begin to change a bit. And this part matters because this is where the models start to be run prospectively. That is, this is the part where the modelers are taking the input data, but they don't yet have the output data to compare it to. And at this point, we now have a 14-year duration where the black line and the red line don't touch each other. But what's more, they're still diverging. This is going to run for a long time by the looks of it. Even if the pause ends and there starts to be an upward trend in the temperature data, it would take a huge amount of warming at this point for the black line to catch up to the red line. I mean, it's for that gap to close in the next, say, 4 or 5 years, we would have to have just a stunning amount of warming to take place and close that gap. And if that doesn't happen, if the pause continues, then they're going to be so far apart that it's unlikely they will ever touch again. That the divergence will be more or less permanent on the current construction of climate models. And that's the new piece of information that matters. So it's not the pause, it's the discrepancy. And the fact that the discrepancy is now longer than it's ever been in the record, and it's still growing. So at the point where the models start to run prospectively, then they don't start working. And that tells us we have some questions to ask about the models as they're currently configured. So why this discrepancy is opened up? See, there were intervals in the past where the model said we should have a pause, and the observations say there was a pause, so that's fine. And then there are intervals where the models say we should have warming, and the observations say there was warming, so that's fine. But right now, what's going on is the models are saying we should have warming, but we're having a pause. We should have warming in the models because from 1990 to 2014, atmospheric CO2 levels went up by 13%. And according to the IPCC report, the way they calculate this in modeling terms, when you put the CO2 change in and the reduction in aerosol levels in the atmosphere, their calculation is there should have been a 43% increase in radiative forcing, which is the way they quantify the effect on temperature of changes in the chemistry of the atmosphere. So that's a pretty big increase in a little under a decade, and that's what plays out in the models as this projection of a fairly rapid phase in surface warming. And with those inputs, the models all agree on what should have been observed. Now, this is a pair of graphs from a recent paper by Fife et al. And the histogram, looking at the panel on the left, the way that's constructed is to take all the models, run them over 1993 to 2012, so a 20-year span, calculate the warming trend that they predicted, and that warming trend then is represented as one of those gray bars. So the gray bar tells you the size of the warming trend that the model predicted. And so there's a distribution of them. Some of them are fairly low, some of them are much higher, most of them are clustered in the middle. And then the red lines, the shaded area there, that represents the observed temperature trend over the same interval. So you can see over the past 20 years, the observations sit right down at the low end of the model distribution. And then the second panel is the last 15 years, and you can see the models are clustering up a little bit higher. Observations are actually moving closer to zero. So the overlap there is disappearing. In the IPCC report itself, as they were discussing this hiatus, as they refer to it, they make the point that 111 out of 114 models predicted too much warming over that 15-year interval. The authors of this picture here point out that over the 20-year span, GCMs, the climate models, predicted 4 times more warming on average than what was observed. Now, there are other indicators beyond the surface average. A really important one has to do with a region of the atmosphere called the tropical troposphere. The troposphere is the layer that goes from the surface up to 16 kilometers over the tropics. It thins to 10 kilometers over the poles. The tropics, first of all, it's a huge region making up about half the atmosphere. But it's also important because that's where most of the solar energy enters the climate system, and some very strong feedback processes operate through the accumulation of water vapor and the ocean and the circulatory system in that region. So models have to get the tropics right. And there's a great deal of attention paid to the performance of models in the tropical troposphere because all the models predict that with this very strong feedback system that they have built in, there should be the most rapid warming of all should be observed in the troposphere over the tropics. Now, these numbers come from Chapter 9 of the IPCC report, and they point out using different systems, the weather balloons and the weather satellites, the observed trend is somewhere between 0.02 and 0.13 degrees per decade. The model range is from 0.15 to 0.41 degrees per decade over that same interval. So now the distributions don't even overlap in the tropical troposphere. One of the papers that they got these numbers from is one that I was a co-author on a couple of years ago, and then I have a new paper that'll be coming out later this summer where we've taken the weather balloon record back to 1958 for the tropical troposphere to see how the discrepancy plays out over an even longer period of time. One of the reasons that someone like me is involved in this is really just time series analysis. And when you do a PhD in economics, you learn a lot of time series econometrics. And there are now actually quite a few economists who are working on climate data sets, partly because they're all tired of working on finance data sets. But also there's a lot of interesting climate data and very interesting time series modeling issues to be tackled there. So it's actually getting fairly common for econometricians to be working on these issues. This is a picture from the next paper that we have coming out. The top panel is for the lower troposphere, the bottom panel is for the mid-troposphere. That staircase of circles with lines through them, those are the 23 climate models used for the fourth assessment report. And what the circle in the middle shows is the magnitude of the warming trend from 1958 to 2012 from those models. And then the error bars are shown around them. And then at the right-hand end, you can see 3 circles representing the observations in 3 weather balloon series. And the model here, we allow for one structural break, which always occurs in the late 1970s because of a climate event that happened. And so this is the comparison of the trends. What you can see, it's fairly obvious there. There's fancy tests that we can do to formalize the point, but you can see that the observations are clustered pretty low. There are some models that get down towards where the observations are, but by and large, most of the models have way too much warming going on in them. And if by any chance you're curious about where the Canadian climate model sits on the graph, it's there. Okay. One other paper that I want to bring to your attention is a very interesting study by a fellow named Kyle Swanson in Geophysical Research Letters last year. He was looking at a comparison between the models used for the fourth assessment report and the fifth assessment report. And the fourth assessment report suite of models are called CMIP3. That stands for the Coupled Model Intercomparison Project number 3. And then the most recent IPCC report used the CMIP5 models, Coupled Model Intercomparison Project number 5. And he did a few comparisons between all the models and observations, looking, and I won't explain this in detail, it would take too much time, but he looked at the spatial pattern of trends across the Earth's surface, and then also at the model's behavior replicating or predicting extreme events, extreme cold and extreme warming events. And in both cases, what he found is between the CMIP3 and the CMIP5 models, they all clustered more tightly around the mean. So they're all becoming more like each other. But in the process, they're also moving farther and farther away from the observations. And now he has a proposal that what's happened is that the one region that the models tended to underestimate warming was in the Arctic. And between CMIP3 and CMIP5, they're all doing a better job now with the Arctic. They're just doing worse everywhere else. And so he thinks that perhaps unconsciously the modelers have been trying to deal with the Arctic situation and not necessarily getting it right, but in the process they've moved farther away from the observations. So he makes an interesting observation here in his conclusion. Curiously, the CMIP5 simulations appear to be approaching a consensus. However, this consensus appears to explicitly exclude the observed warming. And it's the same with the simulation of temperature extremes. Between the 2 generations of models, the models are now like each other, but they've completely moved off the observations, the observational data. Okay, so this, of course, leads to a challenge in the world of climate modeling. If things, and this is a quotation from a senior member of the European climatology profession, Hans von Schork of the Institute of Coastal Sciences in Germany, a well-known climate modeler. If things continue as they have been, in 5 years at the latest, we will need to acknowledge that something is fundamentally wrong with our climate models. A 20-year pause in global warming does not occur in a single modeled scenario. And this is a quote from Judith Curry. She's a climatologist at Georgia Tech. Depending on when you start counting, this hiatus has lasted 16 years. Climate model simulations find that the probability of a hiatus as long as 20 years is vanishingly small. If the 20-year threshold is reached for the pause, this will lead inescapably to the conclusion that the climate model sensitivity to CO2 is too large. So that's the point that we need to dwell on a little bit. That where all this is leading to is not simply, well, we need to do a bit of tweaking with the models, but specifically, it may be the models are too sensitive to CO2. That would be the simplest explanation of what's going on. Now, before the modeling community all rushes to embrace that possibility, they are looking at a long list of alternative possibilities. So there are a whole bunch of hypotheses being explored. Maybe the heat's there, it's just going into the oceans. Maybe the Pacific wind patterns have changed. Maybe there's something going on with stratospheric water vapor. All kinds of possibilities that would allow you to have a high sensitivity to CO2 in the models, but the models still successfully manage to predict a hiatus in warming even during an interval where radiative forcing has gone up so much. So that's what some people are looking for. I'm not sure what the prospects are there, because these would all be major new climate science or climate system features. And they're becoming a long time after we've been told the science was settled, that we cracked the code, we know how the climate system works, debate's over, blah, blah, blah. And now, oh, well, except we're going to have to start building in whole new mechanisms that we never thought of before that completely override the effect of CO2. And, you know, maybe that'll turn out to be the explanation. But really a much simpler explanation in all of this would be the sensitivity to CO2 may just turn out to be too high. Empirically, that would be where Occam's razor would point us. This is data from the IPCC report. This particular histogram is not in the report, but it's just taken, the numbers are taken from a table in Chapter 9. This is a measure of what's called the transient climate response of CMIP5 models. And you can see the number at the bottom. You can think of it as roughly how much warming would you get over a 70-year span if CO2 levels doubled. And so the models are spread out along the horizontal axis with a lot of them piled up around the 2-degree mark. If you take the observations, it says observed there, it's not really observed. What it means is it's what you can infer from observations over the past 150 years. Given the calculations of radiative forcing and the observed temperature change, the transient climate response in observations would be down at the bottom end of the distribution there. So now, if we put that on the table and say, okay, the observations, they're still within the universe of models, but they're way down at the bottom end. What does that mean for the economic analysis? Well, then we have to switch over to talking from climate models to integrated assessment models. Now, integrated assessment models, I'll explain a little bit more about them, but one of the most important parameters in them is the sensitivity parameter, the sensitivity to changing greenhouse gas levels. And the important thing to bear in mind is integrated assessment models are calibrated to match climate models, not reality. So they are not fitted to observations. They're fitted to the distribution of climate models. If the climate models are skewed too high, that just gets inhaled into the integrated assessment models. So integrated assessment models, there are 3 main ones that get used. There's the DICE model from Nordhaus's group down at Yale. There's the PAGE model, Chris Hope over in the UK, and then the FUND model by Richard Toll and his colleagues at Sussex. The first 2 are particularly at fault for just being calibrated to climate models. The FUND model is a little different, as I'll explain. His damage function is much more sophisticated. It is based on empirical measures from around the world, dividing the world up into regions and building up the damage estimates based on empirical evidence, whereas the other ones, their damage functions are just sort of, well, I'll show you what they look like. But All of them use extremely simple economic models and extremely simple climate models. And so there's lots to worry about in terms of how they operate. The three main sources of uncertainty in the integrated assessment models, first of all, the discount rate. So they have to be run over 200 or 300 year spans. And so then the question is, well, if there's some damages due to global warming, but they don't occur for 200 years, how much should they count today? And so that's the discount rate question. Second one, as I've talked about, the sensitivity function that translates the changes in CO2 into a change in temperature, and then the damage function. It translates a change in temperature into changes in welfare or utility through effects on consumption and productivity. And it's those last two steps that really matter. The discount rate, it's important, but it doesn't actually derive the huge range of numbers that are there. Within the standard uncertainties, the integrated assessment modeling literature, if you ask what's the social cost of carbon, the social cost of a ton of carbon, they can nail it down pretty precisely, somewhere between $0 and $206 per ton. So when someone gives you a precise answer and says, well, it's $31, they've made a lot of choices to get a number like that. The range there is primarily a function of the sensitivity and feedback estimates. If we, for instance, if we went with an extremely low discount rate, the range would only fall to between $11 and $206 per ton. So it's really the sensitivity and the feedbacks. Now, I have to show you a little bit of math here. Don't worry if you don't follow it too much, but the damage function, this is from the DICE model, as a percentage of income. So D is the damages, Y is income, and that is just a simple function, and delta T in the brackets there, that's the change in temperature. So in this particular model, whether temperature goes up or goes down is a bad thing. The world was perfect back in 1850, and warming or cooling is bad. Now, the particular function there looks like this, and it's a marvelous thing that they can measure the damage coefficient to 7 degrees of accuracy, or 7 decimal places of accuracy. And you might wonder, how did they do that? What was the, is there an instrument that you can hold up in the air and take the reading? No. This is where they're just calibrating it to the world of climate models. And so they're picking a functional form that gives outcomes in terms of the sensitivity and the damages that would match, roughly speaking, what they see in climate models. Now, Nordhaus's colleague at Harvard, Martin Weitzman, doesn't like that damage function. He thinks it should have a much more exciting upper tail on it, delta T to the power of 6.7, again with an extremely precisely measured coefficient. Then the fund model has its own, it's a little different, but then, the page model. The fund model is the one, though, that doesn't use that approach. It builds it up through regional damage functions, and in fact, some regions benefit, you see, from warming, from historical evidence, and so the fund model is the one that always comes out with much lower damage estimates. And I think that's reflecting the fact that it does take into account that there are some regions that would likely benefit from a little bit of warming. Not to mention any Western cities in particular. Now, Robert Pindyck, who's a well-known energy economist at MIT, looked into integrated assessment models last year and was moved to write, put out a long discussion paper about them and really didn't have much good to say. This is a quotation. "The models are so deeply flawed as to be close to useless as tools for policy analysis. Worse yet, their use suggests a level of knowledge and precision that is simply illusory and can be highly misleading." And the point there is very simple. It's the illusion of people put numbers out and that suddenly it looks precise. Hey, we've now measured the social cost of carbon. No, they haven't. It's just plug some parameters in and crank out some numbers, and if you change the assumptions a little bit, you can get very different numbers out. So it's an illusion of precision. Now, an even worse number is the sensitivity parameter. Here again, sorry, a little bit of math, but the delta T that you see there, that's what the model has in it as the amount of warming you get if you double the CO2 level in the atmosphere. And that's a function of the delta F on the right, which is the doubling of the radiative forcing, which is based on the changes in atmospheric chemistry. And then there are two parameters. Lambda is the basic sensitivity, and F is the scaling factor or the feedback parameter. If F is 0, it just disappears, and all we get is the warming is a direct function of the forcing, and lambda is a fairly small number, so you don't get much warming even if CO2 doubles in the atmosphere. Now, if F goes to 1, then you have a divide by 0 F error, and your delta T goes up to infinity. So we better be able to measure F very precisely because it's going to make a huge effect on the results. So what is F? There we go. F is 0.61. Again, I don't know what the instrument is. You hold it up in the air and it'll measure F and tell you 0.61, although it's not exactly 0.61. It's 0.61 plus or minus 0.44. And if you're doing the numbers in your head fairly quickly, yes, you do get to 1. So there's roughly a 1% chance in an integrated assessment model that a ton of CO2 would raise the Earth's temperature to that of the interior of the sun. Now, of course, they don't publish scenarios where this happens, but what happens is they'll run a whole bunch of model simulations and let the parameters drift around a little and create a distribution. And it's this crazy upper tail that drags the average up. So the long-term trend in the Hadley series, as I showed you, is about 0.8 degrees per century with all the CO2 emissions and everything that's happened. In the models, should atmospheric CO2 double by 2100, the integrated assessment models deem it equally likely that the world's temperature will increase by 1.6 degrees or 23.7 degrees. So they have this big upper tail, and that's what drags the average up in these calculations. If we were just using empirical evidence, that would force the whole discussion down to the low end of the distribution. And so that's what you get when you have one class of models that's calibrated to another class of models rather than the models being calibrated to empirical evidence. And that's the problem that we're in with the integrated assessment models. So, policy implications. First of all, there is new information. So new information has come out roughly in the past 10 years of that ending portion of figure 9.8 that I showed you, that climate models are predicting too much warming in response to CO2 emissions over the past couple of decades. That was not obvious 20 years ago. It is now emerging as new information. Unless there's some clever explanation for this, it's an observation that will be decisively confirmed in the next 2 to 4 years. In other words, unless some way of reconfiguring climate models emerges that has high climate sensitivity and yet no warming over this current interval, Occam's razor is going to bite, and it will turn out that the climate sensitivity to CO2 will have to be dialed down in these models. And that means a major rethink. Either way, actually, it means a major rethink of the structure of climate models and a downward revision to standard sensitivity, either a direct downward revision or the introduction of large natural offsetting mechanisms that weren't thought of a long time ago. So, moving now to the economic models that we use. First of all, it's obvious that they already yield such a wide range of results as to be largely useless and probably misleading for policymaking. But the bigger problem is they're calibrated to the whole distribution of climate models, and in fact, the way they're structured with that little sensitivity parameter in a denominator form, it gives them this huge upward tail, and so they're typically biased towards oversensitivity. And I would say they're, in that respect, they're even worse than the GCMs, the climate models. So they're useful for some things. They're especially useful for looking at the role of the discount rate, just because that's a more objective calculation. But most of the other stuff, they're kind of interesting for thought experiments, but they're, as far as policymaking goes, we have good reason not to take them too seriously, but especially now would be a good time to set them aside until the sensitivity issue in GCMs is closer to being resolved. And it's that point here that I'll wrap up with. So it's not conclusive, but there's a prima facie case at this point that the social cost of carbon has been overstated, because it is based on these sensitivity estimates that right now are running way too high in comparison to observations. But the uncertainties here are likely going to be resolved, and we don't have to wait too long. It's another 2 to 4 years, I would say. If that gap doesn't begin to close, if we get up to a 15 or 18-year gap between observations and it's still growing, then it's pretty clear that models have to be rethought. So that means that we have some new information today that matters, but more importantly, we're going to get new information in the next couple of years that really matters. And there's no downside at this point to waiting for that information before making some big policy commitments. And there's considerable upside, because that's the kind of information that when it comes out can prevent countries and provinces and cities from making an extremely expensive mistake. Obviously, if it turns out that the sensitivity to CO2 is much lower than the distribution of models suggests and the social cost of carbon has been overstated, that's a big factor in what would be an optimal policy response on the CO2 issue. And so that's the kind of information we are going to learn quite a bit over the next couple of years on that point. And that's why there's considerable upside at this point to waiting till that information comes out, and therefore avoiding potentially making a very expensive mistake on climate policy.